In the last video, we saw that the bonding picture for metals is dominated by their very low ionization energy. So, for example, if a bunch of sodium atoms were to come together, their loosely held valence electrons would become detached from the metal cores and sort of float around as a sea of electrons holding the atoms together. And this produces the metallic bonding that's observed in a metal element like sodium. We also saw that if metal atoms come into proximity with nonmetals, for example, if a sodium atom comes near a chlorine atom, again, the loosely held valence electrons become detached from the metal atom core, and this time those valence electrons glom onto the nonmetal, in this case chlorine, forming chloride ion, and this is responsible for the ionic bonding that's observed between metal atoms and nonmetal atoms. So now we're going to turn our attention to the bonding picture when two or more nonmetal atoms come together. So, for example, if two chlorine atoms were to come into proximity, neither one of them is going to want to loosen its grip on its valence electrons, and yet both of those atoms would like to take on more electrons. Chlorine has a very high electron affinity, and so what ends up happening is that the atoms come together and their valence electron clouds overlap in such a way that both of the chlorine atoms are able to share some of those valence electrons. So let's take a closer look at this bonding picture between the two chlorine atoms. And I'm going to start by just reminding ourselves that the atomic nucleus really is infinitesimally small, and so it's absolutely tiny compared to the electron clouds for the core electrons, and also for the and certainly for the valence electrons. But looking at the electron distribution in the chlorine atoms, we can see that each of the atoms retains its electron core. The core electrons are still strongly attached to the nuclei, and that remains true when two of these chlorine atoms come into proximity. The cores stay firmly attached to the atomic nuclei. But the valence electrons, those electron clouds, are able to overlap, and from the exact picture of what happens to those valence electrons becomes very complicated very fast. There's some sophisticated mathematics that we can use to describe the picture, but one thing to keep in mind is that electrons really aren't very smart, and so from the point of view of one of those valence electrons, it doesn't know what an atom is. It doesn't know what atom it came from. All it knows is that there are a bunch of protons that it sees that are attracting it, and there are a bunch of electrons it sees that are repelling it. And so from the point of view of the valence electrons, what they see is basically a large atom with a multi-part nucleus. So it's attracted to the positive bits, it's repelled by the negative bits. And like I said, we can describe this in a mathematical way, but we don't need that kind of detail to understand what's going on between the chlorine atoms, at least to be able to use this. And so we turn to a much simpler picture of what's going on with these valence electrons. This picture was suggested by a chemist, Gilbert Newton Lewis, who was active in the early part of the 20th century. And what he suggested doing to illustrate the disposition of valence electrons around these atoms was to look at the valence electrons on each atom. So chlorine, for instance, has 7 valence electrons. It has a valence configuration of 3s2, 3p5. What Lewis suggested was that we could represent these valence electrons just by putting dots around the atomic symbol. So the idea is that chlorine has a nucleus with a bunch of protons in it, and then there is a core of electrons that is tightly attached to the nucleus, and then on the periphery of the atom, on the surface of the atom, are these 7 valence electrons, and we can represent them just by putting dots around that atom. And typically these dots are drawn in pairs when possible, but that doesn't really matter. The important thing is that there's a dot for each of the valence electrons. And the other important thing is that chlorine has a vacancy in its valence shell. So we know that chlorine would like to take on one more electron and fill in its p sublevel. And so it has a vacancy. I'm going to represent that temporarily with a little open circle to show that chlorine has a space where it could take on one more valence electron. And so if there are 2 chlorine atoms, we can draw Lewis symbols for each of them. And then if you imagine the chlorine atoms approaching one another, their valence shells can overlap, and we could imagine 2 of the electrons being shared by both of the chlorine atoms. And this sort of picture, where we use dots to represent the valence electrons, is called a Lewis structure. And you can draw it in the way that is shown here, with a pair of electrons, a pair of dots being shown in between the 2 atoms. But more often, the electrons being shared between atoms is instead represented by a line. So you'll see pictures like this. But it needs to be understood that a line like that in one of these Lewis structures does represent a pair of electrons that are being shared. And this shared pair of valence electrons is called a covalent bond. Covalent because the valence electrons are being shared. They're sort of cooperating between the 2 atoms. And so that's indicated by a line in the Lewis structure. And you can have covalent bonds with just a single electron being shared, although that is pretty uncommon. Almost always when you speak of a covalent bond, you are talking about a pair of electrons, and this is reminiscent of what we saw when we looked at electron configurations in individual atoms, where we saw that it's always possible for 2 electrons to share a physical space in an atom as long as they have opposite spins. And so that's the same sort of picture here. You can have 2 electrons that are sharing the space between 2 atoms, as long as they've got opposite spins. And so you can have a pair of electrons being shared, and that shared pair of valence electrons is what we mean when we speak of a covalent bond. So I want to look at a couple more examples to just show you how this pattern plays out. So the next example I want to look at is the molecule called ammonia. It has the formula NH3, and I'm going to construct its Lewis structure in a systematic way. And I'm going to start by writing the Lewis symbols for the atoms in this molecule. So we've got nitrogen. Nitrogen has 5 valence electrons, and so I put 5 dots around the letter N in the Lewis symbol. And then there are 3 hydrogen atoms. Hydrogen has a single valence electron, so I put 1 dot on the H's. Once I have identified the atoms that are involved in the molecule, I arrange the atoms so that the covalent bond can be made. So we arrange the atoms in such a way that a pair of electrons can be shared between neighboring atoms. So I'm going to put the nitrogen sort of here in the middle. I'm going to bring this hydrogen over here. I'm going to bring this one around there and move its electron over. And then I'm going to move this guy down and bring its electron up. So now the atoms are arranged in such a way that between neighboring atoms, there's a pair of electrons that's able to be shared. And then finally, I'm just going to use lines to represent those covalent bonds. So each shared pair of electrons I'm going to represent by a line. And so this would be the Lewis structure for ammonia, for NH3. Now, there are other ways that we could imagine drawing the NH3 molecule. For instance, we could imagine just stringing the atoms together like this. All the valence electrons are here in this picture, but this is not a satisfactory picture of the ammonia molecule for a variety of reasons. For one thing, if you look at the Lewis structure that I drew up above, if you count the electrons that are around that nitrogen atom, it has 2 electrons that are still being shown by dots, and then there are 3 pairs of electrons represented by lines. So altogether, that nitrogen has 8 electrons around it, and so it has managed to fill in its valence shell by forming bonds to hydrogen. In the picture down below, the nitrogen atom only has 5 electrons around it, and so it hasn't been able to fill up its valence shell in this picture. It still has 3 vacancies. So the nitrogen atom is not happy in this picture. Another thing that is unsatisfactory in this picture is that although we do have electrons being shared between the atoms, there's only 1 electron being shared between neighboring atoms here. And so if you think of these covalent bonds as electron glue that holds atoms together, there's only 1 electron gluing the atoms together in each of these connections. And that's just not as satisfactory as having a pair of electrons holding 2 atoms together. And furthermore, we can't even put more electrons in between the atoms, because hydrogen only has room for 2 electrons in its valence shell. Hydrogen has its valence shell is just the 1s orbital, and so we can't even put more electrons in to those bonds because hydrogen doesn't have room for them. So this bottom arrangement of the atoms is not a satisfactory arrangement, and instead ammonia adopts the structure that is shown up above, where you have a nitrogen atom in the center, and then the 3 hydrogens are arranged around it. Let's look at one more example, and this is the molecule methanol, which has the formula CH3OH. And again, we're going to start out by writing Lewis symbols for the atoms in the molecule. Carbon has 4 valence electrons. Hydrogen, again, has 1 valence electron, so we've got 3 of those. And then oxygen has 6 valence electrons, and then we've got the last hydrogen. So these are the atoms in our molecule. And then once we know what those atoms are and we know how many valence electrons they have, then we can arrange the atoms so that we can make the covalent bonds. And so this is what the arrangement would look like. And so I've just moved the atoms into position so that the electrons can be shared between the atoms. And then we use lines to represent those covalent bonds. And so this is what it looks like. And this would be our Lewis structure for CH3OH. And again, we can imagine arranging the atoms in other ways. For instance, we could imagine having having 2 hydrogens attached to the oxygen atom and 2 hydrogens attached to the carbon atom. And at face value, this looks like a reasonable picture. We've got, every bond consists of 2 electrons, and so that's good. And each of the atoms has managed to fill up its valence shell. Hydrogen has room for 2 electrons, and each of these hydrogens is sharing 2 electrons, so the hydrogens are all happy. Carbon and oxygen here want to have 8 electrons in their valence shell, and they've got that in this picture. So, so at first glance, this looks like a reasonable arrangement of the atoms in the methanol molecule. However, this is not how the atoms arrange themselves, and one way to see why that is if we imagine sort of working backwards and replacing the lines with electron pairs, and then thinking about how we would split this up into individual atoms. If we were to just separate the atoms, the carbon would end up with 5 electrons around it, and the oxygen would also end up with 5 electrons around it. And that's not how many electrons carbon and oxygen have. A carbon atom by itself has 4 valence electrons. An oxygen atom by itself has 6 valence electrons. And so the valence electron picture of the separate atoms is not consistent with this arrangement of atoms in a methanol molecule. So this doesn't really work, and this is not how the atoms are arranged. Similarly, we could imagine putting 3 hydrogens around the oxygen atom, but again, if we go through the same sort of mental exercise and imagine thinking of each bond as a pair of electrons and then splitting up the atoms, again, this picture is not consistent with what the atoms look like by themselves, and so this is not a good picture of methanol either. So we'll look at some more examples in the next video and develop some more ideas, but for now, that will be it for this time around.